Okay, so here we see 6 plots. So two of them, so each of them shows 3 solutions of a first order differential equation. So two of them are autonomous, 2 are linear homogeneous, and 2 are linear non-homogeneous. So let us determine which is which. So first of all, the easiest to determine is a linear homogeneous, right? So what is linear homogeneous? So a linear homogeneous first order equation is a prime plus p of t times y equals, well, if it were non-homogeneous, we would have some non-trivial right-hand side. Homogeneous means that it equals 0. Right, so the general theory of differential equation tells us that the set of solutions of this is a one-dimensional vector space. And so one-dimensional vector space. Now, what does it mean? So vector space means that the sum of two solutions is again a solution. And if we multiply a solution by a constant, then we again get a solution. So one-dimensional vector space means that actually all vectors are proportional to the same vector. So geometrically, it means that all solutions are constant multiples of one another, or are proportional to each other. Proportional to each other. Well, and it is very easy to see. So in plot A, all solutions are proportional to each other, and in plot F, all solutions are proportional to each other. So all of them are constant multiples of each other. So you can imagine that, I don't know, if a solution is plotted on a transparent rubber sheet, then if you kind of stretch this rubber sheet, then the curve becomes kind of more stretched. But it follows the same basic path, but it just becomes more stretched. So this is what we see in A and F, right? So in A and F, they're linear homogeneous. Well, then, how about autonomous? So autonomous are actually, now, the problem is that linear non-homogeneous are often, I'm not sure if there is a generic way to identify a linear non-homogeneous equation. I don't think that there is any. So we can't really, there's too much kind of freedom in a linear non-homogeneous equation. So we can't really identify it. So we've got to identify autonomous equations. So in autonomous equations, so recall that in autonomous equations, though, the main property of autonomous equations is that it is invariant under horizontal translation, right? So invariant under horizontal translation. So if we have any solution, then if we kind of make a copy and move it to the right, or make a copy and move it to the left, then we get another solution. Now, which of these pictures fits into this? So obviously B. In B, all these solutions, they are horizontal translations of each other. But also notice that E is kind of like this, because in E we have two solutions that are horizontal translations of one another, and there is a constant solution. That is also possible for an autonomous equation. So B and E are autonomous equations. So which means that the remaining two are linear non-homogeneous. So these two, C and D, are linear non-homogeneous. Linear non-homogeneous. Now, maybe we have solved the question, but maybe let me comment a little bit more about what we see in plots C and D and how it fits into the paradigm of a linear non-homogeneous equation. So D, as a matter of fact, in D, all these solutions that we see, they are vertical translations of one another. And while vertical translations of one another, it means that the general solution of D looks like, well, some specific function some function of t, plus constant, and changing this constant, we get different solutions. But this is a very familiar pattern, right? So this is just integration. So when you do integration, you always add plus constant. So what you see in D is that you see that this is a differential equation of the type y prime equals some given function, say f of t. And solutions are just different antiderivatives of f of t, and they differ by a constant, by an additive constant. And this is certainly a linear non-homogeneous equation. Now, this is D. So actually, by the looks of D, we can certainly claim that this is a linear non-homogeneous equation because it is just of the form y prime equals f of t. C is trickier. So what we see in C is we see a parabola, and we see other solutions sort of approaching this parabola. So we see that the general solution is probably some t square over, I'm not sure what the coefficient is, I don't know, something. Let me just try t square. So I'm not, we cannot really see the scale of the y-axis here, so I'll just write t square. So this is the red parabola. And other solutions approach this parabola. Now, while there could be many ways to kind of try to get this pattern, but I guess it is a safe bet, kind of maybe I'll write seems like this is t square plus some constant times something that approaches 0 if t goes to infinity, and something that approaches infinity when t goes to negative infinity. So usually it is e to the negative t. It may be e to the negative 2t, maybe something more complicated, but it is something like this. So which means that the general solution fits into this pattern. So some specific form plus constant times another specific term. And this is a linear non-homogeneous equation because this is the particular solution of this non-homogeneous equation plus general solution of the homogeneous equation. So which is how we kind of see that it fits into the paradigm of a linear non-homogeneous equation. Although I agree that in C it is probably kind of harder to see it, and the safest way is to just, once we have established that A and F are linear homogeneous, and that's for sure, B and E are autonomous, and that's also for sure, then we just, the remaining two must be linear non-homogeneous.